Record. So does someone want to monitor like the chat if there's a question, and then let me know if there's a question, because I can't really see it that well?
Yeah, I can.
Okay, super. All right, so what we did before the midterm was we talked about the different the different ionization techniques. And what were some of the different ionization techniques in mass spec? Anybody? There were a couple of them.
Like Sims, Fab, and Maldi.
Okay, right. So there were the desorption varieties. This would be Sims, Fab, and Maldi. So Sims, so Maldi was a laser. Fab was fast iron bombardment. So it was usually like a xenon or argon, and then Sims was you're hitting it with a cesium ion typically. That was one type. There was a couple other types. So this one, your sample would be in a matrix of some type, and you would hit it with either your laser, and then as the ejected matrix would transfer charge to your sample. And so this was used for basically larger molecules that you couldn't put into the gas phase. And the matrix tended to be this matrix. Some of the things were like glycol, or varieties of glycol, thiol glycol, that sort of stuff. What were some other ionization techniques?
Could be chemical ionization.
Right, there was chemical, and then the chemical ionization, and the one which was similar to this would be the electron impact or electron ionization. So in the electron one, you've got your molecule, and it gets hit by some high energy electrons, and it strips off an electron. So you end up with mass, you end up with a radical cation because it's lost an electron. Your sample's lost an electron. With chemical ionization, the only difference is that there's a carrier gas in there. So you've got some gas, typically things like NH3 or methane. And instead of losing the electron, quite often your sample gets protonated. So it has got a positive charge through protonation. So those were some of the ionization techniques. So you either have got a radical cation or protonated species, which is a cation, of course. Now, in like the various, the key part in mass spec is that to be detected. The sample must be charged. So if you've got if your molecule is a radical cation, this will be detected. If it is like mass plus H, and it's got a positive charge, this would be detected. So you have to have a charge, and there's actually ways of putting a negative charge on mass, particularly in some of the quadrupole mass specs like the ion trap. You can actually put a negative charge on your sample if you want to, but it's but the more often than not, it's got the sample itself is going to bear a positive charge. So it's going to be a cation of some type. So the sample must be charged. That's the key part to what we're doing. Now, if you remember what a mass spec looked like, we had, what was the x-axis? What was that? There was a whole bunch of numbers here, like 10.
Mass over charge.
Yes, MZ. So mass to charge ratio, right? Okay. And what was the y-axis?
Relative intensity.
Right. Okay. Relative intensity. Relative intensity. Okay. So if we had some peak here, which had this is 100%. The peak here at 40, which is at 100%, that had a special name for it.
Is that the base peak?
Right, base peak. So the base peak is the most abundant peak in the spectra. So all other peaks are measured relative to that. Now let's pretend that we had a little peak way down here at 70. And this has got a special name, the M plus peak, or the charge peak with the highest mass. This is what? The peak which results from the loss of a single electron. This peak had a special name. So whatever your molecule was, it loses an electron and it gets charged, and it comes out at the highest mass to charge ratio. Its special name is the
molecular ion.
Right, molecular ion. Molecular ion. Good. Now, on occasion, you sometimes see a peak which is slightly larger than the molecular ion, and it might be like a M+2 peak, and this results from what? When you've got a peak which is actually more, which is atomic mass is, or molecular mass is actually larger than the molecular ion peak. Where does that come from?
Isotopes?
Right, isotopes. So isotopes. So there's isotopes. So there's two isotopes in particular which we should talk about, like bromine. If you look on a periodic table, the mass of bromine is 79.9 or something like this, blah, blah, blah. So it has two isotopes. The light isotope is 79 and the heavy isotope is 81. And so the average comes out to be just under 80, but the natural abundance of these two isotopes is essentially 1-to-1. So in a mass spec, you can tell if a bromine atom is there really easily because you'll see two peaks, like the mass and then the mass plus 2, and they'll basically be a 1-to-1 ratio in height. So bromine is the most common atom, which has got like a really large M+2 peak. Chlorine also has got M+2 peak, but the ratio for chlorines is 3-to-1. So if you've got your mass here, if there's a chlorine atom, this M+2 peak, M+2, is basically 1/3 of the so chlorine is similar, but the ratio is slightly off. So the lighter isotope is 3-to-1 heavy. And then I guess the other part is nitrogen. The rule, nitrogen, if your atomic mass is odd, and we're talking about, like for example, say it's 121, then then you know you've got a nitrogen because it's an odd number. You should have an odd number of nitrogens there. But with regard to isotopes, it's really bromine and chlorine, which have got the two large ones that you can see quite easily. Sulfur's got a S+2 peak, but the ratio isn't anywhere close to this, so it's usually just a tiny little thing you would see in addition to it. Okay, let me see. What else did we talk about in the last class if we're just reviewing things? Okay, yeah, and if there was a peak like here, I don't know, at 55, or another peak at 25. So in this case, the base peak and these other peaks, they are all fragments of the original molecular ion. So your molecular ion so it gets charged, so you lose an electron, and then this molecular ion can then break apart, and there's a couple of different ways it can do that. And this is, I guess, what we'll try to talk about today. So it could break apart into, say, two fragments. One way it could break apart, and so you could make fragment plus and another species here, like say R radical, or it could break apart this way and say F radical plus R plus, or it could break apart. Third way is that you could form a neutral compound and have a new species, we'll call this O, which is a radical cation. So when your molecular ion breaks apart, it can break apart in a variety of different ways in which two of the species, one species is a radical, one species is a positive charge. And I've just reversed it here over here with the radical positive charge. Or you can break it apart where one of the species is completely neutral. And in those cases, the part which is the second fragment is going to be a radical cation. So if we're thinking about what gets detected through all of these fragmentation processes, it's only the charged species. So in this case, in case number 1, the F plus would be detected. In case number 2 here, the R plus would be detected. And in case 3, the O with the positive, and this would be detected. the neutral molecule wouldn't be detected. The radicals themselves wouldn't be detected because they don't have a charge associated with them. So if we think about the easiest one, if we're thinking about radicals here, just think of the methyl radical. And if we do the formal charge on this, so formal charge equals number of valence electrons it would normally have, which for carbon would be 4, minus the number of bonds, 1, 2, 3, minus the number of free electrons, which in this case is 1, which equals 0. So it's got no formal charge. So radicals are super reactive, true, but in this case, it doesn't have a charge associated with it. Okay, so then what we're going to do next is we are going to sort of, well, what I wanted to show you today was some common ways in which molecules fragment. So my next question is, let's see, let's put a colored thing here. So let's pretend that you're a radical cation and you are forced to break apart or forced to fragment. What species would you form if you were to break apart? What would be the yeah, I'm trying to just say what would be the species that you would form preferentially over other species? So in nature, do we form high energy things or do we form low energy things if we are given a choice and we wanted to roll downhill?
It'll form lower energy.
Right. So when it comes time to for a molecular ion to fragment, there's a simple rule in mass spectrometry called Stevenson's rule. Which basically states that the most probable fragmentation is the one that generates the most stable positive charge. So it's the most probable fragmentation. Obviously, when things break apart, there are different pathways. And so sometimes you transiently might form a higher energy one, but statistically, in the law of averages, the most probable fragmentation is the one which generates the most stable positive charge. So let's think here. So for those of you who have taken organic 1 and 2 before, what were some rules with regard to carbocations?
The more substituted the carbocation is, the more stable it is.
Right. Okay. So more substituted. More stable. So if we can, so what do we mean by this? So if we've got a little, like this guy, has got no alkyl groups, this will be high energy. Whereas a carbocation, which has got 3 alkyl groups, will be lower energy. And so if you can form, this would be like a tertiary carbocation, where this would be a methyl carbo, whoops, I've got 2 positive charges here. Oops, let's just erase this. So fragmentation patterns that would generate a tertiary carbocation are way more probable than one which would generate a methyl carbocation. So that's basically, the more substituted the carbocation has, the more stable it would be. What are some other things that help stabilize carbocations? Carbocations can be stabilized by?
Resonance.
Right, okay, resonance. Perfect. Okay, so resonance. So there's 2 different groups in which we can have resonance structures here or here. So the carbon beside a double bond has got a special name. It is the blank carbon. It starts with A. And rhymes with allylic. So, and this would be like the benzylic. So both of these charges can be stabilized by resonance. So benzylic carbocation, so a positive charge beside an aromatic ring, this is stabilized by resonance. A positive charge beside a double bond is also stabilized by resonance. So fragmentation patterns which generate benzylic fragments or allylic fragments would also be relatively popular, because you've got you can draw a resonance structure for, remember, resonance provides stability. So this would be stabilized by resonance, and this positive charge can be delocalized. Or I shouldn't say, this positive charge can be shared over the entire ring here. So with Stephenson's rule, basically the most probable fragmentation is the one which generates the most positive charge. So tertiary carbocations, benzylic or allylic carbocations would all be, so you could basically make a chart from more stable to less stable, or more probable to less probable. Right, now the one thing to keep in mind is that this is where, as a these ionization processes, particularly the electron impact or electron ionization, is super high in energy. You're providing lots of kinetic energy to the molecule, so it can fragment in other ways. So some of our normal rules of things are kind of broken because there's so much energy involved when these things break apart. But my next question is, because I'll show some of the ways that these things break apart. But my next question is, which electrons or which electron will be removed during the ionization process? And what I mean by that is that, okay, so we could have electrons that are in sigma bonds, we could have electrons that are in pi bonds, we could have electron lone pairs. Electron lone pairs are often abbreviated N for non-bonding electrons. Which one of these do you think would be the easiest to be stripped from the molecule? Or if you had to rank them from easiest to, which would be the hardest to remove from a molecule?
Sigma?
Sigma, right. Because they're in the, remember the sigma bond, if you've got two carbon atoms, the sigma bond electron density is basically right in between those two. It's supposed to be in the plane of the bonding axis. So these should be the hardest to remove. Now, if you've only got an alkane where there's only sigma bonds, well, that's the one which is going to be removed from. But these should be the hardest ones to remove, right? Okay, so then, so these would be the hardest. Then, if we're talking about pi electrons, remember the pi electrons are above and below the internuclear bonding direction, or a lone pairs. If you've got, say, an oxygen, say we got a double bond here, you'd have some lone pairs sort of off in the various orbitals that they would be located in. So which one do you think would be easier to remove?
I think lone pair electrons would be easier.
Yeah, it turns out that's correct. So the lone pair electrons, they're not involved in any bonding, right? So unless they're delocalized because of some resonance structure, they're just basically they're off by themselves. So typically, lone pair electrons are the easiest to remove. Pi electrons would be the next, and then the hardest would be sigma. So I think in the last class, we basically had a chart of which type of functional groups survived. Like if you were to ionize a molecule which had functional group A, B, C, or D, which ones actually survived to make it to the detector before they fragmented. You'll notice that a lot of the functional groups that had heteroatoms were ones which didn't last a long time. So it's these lone pair electrons that tend to be ionized first. So if we had something like, I don't know, let's draw. Let's draw an amine here. If this was to get ionized, so minus an electron, it would be, the reasonable assumption would be that you would end up ionizing, removing one of the lone pair electrons to generate something like this. If you had a double bond and you were to lose an electron, you would lose it in between. So one carbon would have an electron, and the other carbon would now have a positive charge. So where the double bond is, you would then have a radical cation in that sort of fashion. And if you had just a single bond, sigma, like, we can't really draw these very well. So if we were to lose an electron, because in Lewis structures, a bond equals 2 electrons, right? So if we were to try to draw this, there isn't a good way to draw it. Like, you could sort of draw like a dashed line like this, but often what the textbooks do, because it's hard to draw little dashed lines, is they just put this whole thing in brackets and say radical cation. Say that somewhere one of these sigma bonds is missing an electron. But if you wanted to specify that it was this bond here, you could, I guess you could do something like that. And then put radical cation, something like this. So lone pair electrons tend to get removed first, then pi electrons, and then sigma bonds. All right, any questions on that so far? Okay, well then what we'll do next is let's talk about just some of the ways that these things fragment. So as I said before, at the top here, there's a couple of scenarios where you've got you could generate like F plus and R radical, or the inverse thing, F radical and R plus. We'll see how that basically works here. So let's talk about, let's put another color here. Let's do blue. Something called alpha cleavage. So this is a radical way of breaking bonds, and it's sometimes it's called site-initiated cleavage. So let's pretend that we've got an ether. So and let's lose an electron. I might actually need to draw an extra carbon here. Yeah, let's do that. Okay, so with this radical site-initiated cleavage, or alpha cleavage, so if we're doing radicals, remember movement of radicals is this little fishhook arrow here. So what we're going to end up doing is breaking bonds using this fishhook arrow, and we're going to generate a positive charge and a radical. And so we can move one radical here, and then we're going to break this bond, and then we're going to generate a radical there. I guess I didn't need to actually draw an extra carbon. I was missing something there. Okay, so, and this would give us this as a fragment. So this fragment would be detected, and this fragment would be not detected. So this would not detect. Misspelling. And there would be another way of doing the exact same thing, except using, let's see here, let's do orange. We could do the same sort of radical cleavage on the other side. And this would generate again, it would be this species which is detected, and this R prime dot would be undetected. So although it's kind of a misnomer calling this alpha cleavage. So this carbon right here, or this carbon right here, is technically the alpha carbon. The heteroatoms here, one carbon over would be the alpha carbon. The second carbon would be the beta. So you're actually breaking the bond. The bond that's being broken is the bond between the alpha carbon and the beta carbon. So that's what's being broken in each case. And so you can do similar sort of fragmentations for, so this was with an ether. What we can see is that similar things can happen with alcohols or amines or thiols, any of those orthiol ethers, any group which has got some lone pairs, and you remove one. So you can break by just pushing arrows, the similar way that I did with the fish hooks. You can fragment along either bond like this. Let's do one with a carbonyl, because it's very similar. Carbonyl. So we've got a ketone, and it's lost its lone pair electron. And what we are going to do is we are going to break this bond or this bond, moving the arrows exactly the same way we did before. So if we are doing this with the yellow arrow this time, let's go here, this goes there, this goes there. And this will generate R. So the charged species will be detected, the R prime dot won't be detected. And then you could do the exact same sort of pattern on the other side, which is green this time. And have R radical, R primed plus. And so what we're going to see is that for functional groups with heteroatoms, this sort of alpha cleavage is a popular fragmentation pattern. Does everyone see how moving these little arrows? So do I have a way of doing a spotlight here? I don't think I do. Does everyone see how, does my little cursor, does this thing, is it showing up on the screen when I move it around?
No.
No.
Move it directly to see.
Pardon?
Can you move it? No, it just shows what you're drawing. That's it.
That's too bad. Okay. All right. So does everyone? So if we've got fishhook arrows coming together like this means we're making a bond. And if we've got fishhook arrows going apart and there was a bond in between, this means that we're breaking a bond. So in this example over here with where these two yellow arrows are here, this bond's being broken because one fishhook arrow is moving on to the R primed, the other one's going to make a bond, and then this lone pair electron is, or this lone electron is coming down to form a bond to make the triple bond here. Does everyone see how the bond making and bond breaking using these fishhook arrows works?
Yep.
Okay, good. So that's one way of doing, let's do this. Actually, this can also apply to pi pi bonds. So if we've got and this gets ionized, so we are going to lose an electron. So I'm just going to use I will put the plus here and the radical here. This color is very psychedelic there. So now if we want to do alpha cleavage on this, so remember what we're going to want to form is the most stable positive charge. So here we can actually make a allylic cation. If we move these electrons to R and these electrons here and these ones here, what we end up getting is, stop that, R dot and then this is of course stabilized by resonance. So you can do this this alpha cleavage even with structures which don't necessarily have a heteroatom. Although that's the most common place for it, there is this possibility with pi bonds as well. Everyone happy with that? Now, so this cleavage method uses fishhook arrows, so we're talking radicals. The second common type is what we would call inductive cleavage, And in this case, if we're doing it mechanistically, we are moving 2 electrons. So to give you a heads up on this, we'll use ethers again as our example. So let's draw it like this. We'll continue this on, because class is almost over. We'll continue this on Thursday. We'll go over the test on Thursday as well. But in the inductive type of cleavage system, rather than moving fishhook arrows around, what we're going to do is we are going to move the electrons in a sigma bond to the positive charge. So in the case of oxygen, it's an electronegative atom. Why wouldn't it want those 2 electrons, right? So in a fragmentation pattern like this, what happens is that R just lost those 2 electrons, so it has a positive charge. And the species that is neutral is now this species here, because we're moving this yellow arrow is moving 2 electrons onto oxygen. So now oxygen has got 5 electrons, non-bonding electrons. So remember, oxygen's, to do the formal charge on oxygen here, normally it's 6 valence electrons minus 1 bond minus 1, 2, 3, 4, 5 electrons equals 0. So this radical is not charged, and this R plus will be detected. And so you could also have an inductive cleavage on the other side if we wanted to draw that. Let's use this green arrow. And we would form plus R prime with a positive charge. And so in comparing the two inductive sort of methods here, if you had an ether and they were asymmetrical, so different things on either side, the more probable fragmentation pattern, could just compare the positive charge of R prime versus R. Is one of them tertiary, is one of them secondary, that sort of stuff. And that fragmentation pattern could be, would happen more with a higher probability, that type of stuff. And so you can do similar sort of things with carbonyls, for example. So in this case, if you've got you can break bonds here or here through this sort of inductive way of doing things. Let's see here. Yeah, the way to draw this is a bit wonky with regards to you've got to move these. It's sort of it's not, the organic chemist in me always has problems with this because I want to do things a certain way, but you can break this bond or this bond, and you've got R plus, and then the rest of your carbonyl here. But let's draw it like this. Let's do it in 2 steps. Put the 2 electrons there, and then move those ones over there because it's got the positive charge. And that's there. And there's no formal charge on this carbon because the carbon's got 4 valence electrons, minus 2 bonds, minus 2 electrons equals 0. It just looks very, the organic and chemist in me hates this look, the way that this thing looks. But anyway, you can break bonds on either side through this inductive cleavage of carbonyls. We've got to find a better way to draw that. But what we'll do is we'll get into, so we'll see that so with carbonyl compounds, and remember we've got different groups on either side for all our different functional groups. This type of process can take place quite commonly. The last part, which we don't have time for right now because I've sort of run over time, is the fragmentation pattern, which gives us, where is it? These species right here. to generate a neutral molecule plus keep the molecule, the fragment as a radical cation, that involves breaking more than one bond at once. So those are special fragmentation patterns, and I'll give you some examples of that on Thursday. It's basically a two bond cleavage. Okay, any questions before we go?
Yeah, can you post this sheet here to Moodle?
Yes, I've recorded it, so I'll just put that up in the Top Hat lecture. Does that make sense? Would that work?
Yeah, that works. Thanks.
Okay. I think that's everything. Okay, so on Thursday we'll talk a bit more. What we sort of did on with the infrared is we basically did a survey of all the functional groups and what are some of the things to look for. We'll do something similar for mass spec. It can be a little tedious at times, but hopefully with a little bit of practice, with mass spec, there's a few things that we can look for which will give us a whole bunch of information right from the start. And then we would use like the infrared and in the future NMR to dig down to what we're looking for. So, but I wanted to show some of the ways that molecules fragment, and that can give us some clues with regard to some of the structural features of stuff or what functional groups we've got. But anyway, we'll get into that on Thursday. Okay, I will end sharing of the screen. So unless there's some other questions, as I said, I'll get the midterm marked and I'll get the assignments marked for Thursday. But until then, have a good couple days.
Hey, Dr. Hill.
Yes.
This isn't related to what the lesson was today, but I forgot to submit my assignment on Friday. I do have it completed. Is there any way I can submit it late and just take doc marks or something like that?
Yes. Do you want to?
I can email it to you if you want or whatever.
Can you make it into a PDF and email it to me?
Yeah, I'll do that right now.
Okay. Thanks.
Okay, have a good day.
You too.